Imagine standing at the crossroads of technology and precision, where vibration signals reveal the health and heartbeat of machines. Today, we'll explore waveform patterns and amplitude modulation, understanding how they shape vibration analysis and gear diagnostics. Waveform patterns form the foundation. Each vibration signal starts as a waveform, mapping motion over time. The shape of a waveform tells us about machine activity, steady, erratic, or pulsing with flaws. Analysts use these patterns to identify issues, prevent breakdowns, and ensure reliability across industries. The waveform is more than a squiggle. It's a story encoded in peaks, troughs, and rhythms. A simple sinusoidal wave shows regularity, signaling a smooth-running motor. Sharp spikes can indicate impacts or faults. As complexity increases, waveforms mix frequencies, illustrating combined forces within machinery. Amplitude modulation is our next focus. Amplitude represents the height of a wave, the signal's strength. Modulation occurs when amplitude changes due to another signal, often from interacting components or defects. These variations are not random. They reveal clues about underlying mechanical events. Imagine a gearbox with a worn tooth. Instead of a uniform pattern, modulated waveforms appear, amplitudes waxing and waning with rotation. Regular beats overlay bass vibrations, creating a pattern that repeats at the fault frequency. Visualizing amplitude modulation. Two waves, a carrier and a modulating wave, combine to show synchronized amplitude changes. The resulting waveform exposes amplitude changes in sync with machine cycle events, revealing mechanical irregularities. Analysts recognize these patterns as fault signatures, guiding maintenance decisions. Amplitude modulation typically appears when a primary signal interacts with a periodic mechanical event. The dominant frequency, the carrier, is enveloped by lower frequency modulations, visible as sidebands in spectral analysis. Sidebands are unmistakable signs of modulation and critical for diagnosing mechanical faults. Gears introduce complex interactions. The meshing of teeth creates cyclical forces, sometimes imperfect due to wear or misalignment. Irregularities modulate vibration amplitude, producing distinct patterns that reveal faults. In gearboxes, amplitude modulation acts as a diagnostic beacon, highlighting fault-related frequencies. Imagine a gearbox with a chipped tooth. Each rotation causes periodic amplitude surges, creating distinct modulated waveforms. This results in a bass frequency surrounded by sidebands at intervals matching the fault frequency. Analysts interpret these sidebands to narrow down defect causes and locations. Visualization accelerates understanding. Analysts use waveform plots, spectrum graphs, and animation overlays to highlight amplitude modulation. Combined with cinematic music and minimalist visuals, focus remains on the science, supporting clarity and insight. To summarize, waveforms paint the picture. Amplitude modulation frames mechanical events, especially in gears. Mastering these concepts allows professionals to detect, diagnose, and resolve machine problems before breakdowns. It's a journey from signal patterns to actionable insights, underpinning vibration analysis for industrial reliability. Every detail in a vibration signal, every modulated beat, every sideband contributes to the story of machine health. Understanding waveform patterns and amplitude modulation equips you to confidently diagnose machine health, especially gears. With these tools, turn signals into solutions, protect assets, and drive operational excellence. Continue advancing expertise, one waveform at a time,